Okay, good morning. So I'm going to review and talk about throttling device and the relevant calculation related to throttling device and how it is related to especially to refrigeration. So please ask question along the way if you have questions. This is one of the equipment which we have discussed so far as it is related to air conditioning system or refrigeration, right? So you know what a throttling device, we have discussed the equation as well. So we are going to see how it is related to Joule-Thomson coefficient. So yesterday we discussed about the refrigeration cycle. So throttling is here. So that's what we are going to be doing now. So throttling to evaporation is the key to the cooling process inside the air conditioning system, okay? Or refrigeration probably. So we discussed this cycle as well. So I think I'm going the wrong way. Okay, so you remember this equation? So we start with this. Remember, throttling is an isoenthalpic process. So delta H equal to 0. If we assume there is no heat loss, there is no work down, it is steady state, there is no height differences, and there is no velocity differences. So it remains we have isoenthalpic process, delta H equals to 0. So if you're being asked why you have this delta H equal to 0 for a throttling device, then you go back to this mass and energy balance equation, and you have to understand again the meaning of all in each and every single term of this equation, okay, which we discussed a few weeks back. So now let's look at the throttling system, and we are going to look into this, which is the Joule-Thomson coefficient, which is related to how the process of gas expansion in a throttling system can result in cooling. But you also remember that it is not only cooling, it may also result in heating if we are not careful in selecting the operating parameters. Okay, so remember this equation. So let me just go to the next slide. Okay, so we have the mu Joule-Thomson. You remember mu Joule-Thomson? Coefficient of Joule-Thomson, JT, two guys, Joule and Thomson's. This is, let me use a different chalk color. Delta T over delta P H as parameter, or if you remember your calculus again, this is in the limit of pressure goes to 0, meaning in the limit of very low pressure, we have delta T over delta P H. Now, I have to ask you, do you remember what is the meaning of the subscript H? Subscript meaning the H. So yeah, that's constant enthalpy, right? So that H, remember in when we talked about the uh, mathematical equation in differential equation, right? Partial differential equation. So that subscript means it's constant. Now you go back to this equation again. So that is how it is related. We have this equation, and for a throttling device, it so happened that delta H equals to 0. So this subscript remains true. Now, you also have to remember that delta means changes. So delta T over delta P, right? So now let's look at, let's say we have a throttling system in here. So of course, in a throttling process, is it from high pressure to low or low to high? So this is high pressure, right? High pressure side. This is low pressure. So let's call this P1, P2. Of course, P1 will be larger than P2, right? By definition, this is a throttling device. So in a throttling device, since P2 is less than P1, is delta P positive or negative? Negative, right? Because this is just P2 minus P1, right? So delta P must be, sorry, less than 0, i.e. negative, right? So this delta P has to be negative. What about delta T? For delta T, what we want is, let's say we want cooling process. Cooling meaning, of course, T2 minus T1 must be positive or negative? Cooling? Negative, right? So this is also negative. So now we have these two definitions. Let's divide, right? Why divide? Because I'm trying to link it up with that, right? Delta T over delta P. So if this is negative, This is negative. So mu Joule Thomson for cooling must be positive, right? Must be positive to result in cooling process. Okay, so that's why when you design a refrigeration unit, you look at the operating system, the operating parameters that you decide. It has to have mu Joule Thomson positive. If we have the throttling, mu Joule Thomson is negative, what do you think will happen?
Start heat up the liquid before.
Instead of cooling, you have heating, right? So that's exactly the opposite, but it doesn't mean it is useless. It may be useful in some areas. So, but for cooling or refrigeration, you will need Joule Thomson coefficient to be positive. Okay, so the high pressure gas and then go to low pressure gas. As the gas expand, we should have cooling coming out, cooling results by the end, and not heating, because you may end up having quite the opposite. Okay. Now, if we look at this picture, this is a picture which you saw when we discussed physical chemistry. We are trying to explain why is it that in a throttling device, when you have expansion, you can have cooling or heating. Okay, so let's look at this. So let me exchange the board. Okay, so let's look at this. Remember, the gas, if we have molecule of gases, we may have repulsive or attractive forces, right? So if you look at this picture, remember the x-axis is distance. So if the two molecules are very far away, r is at infinite, let's say the r is distance between molecule. The molecule is, they don't care about one another, right? One is in Bandung, the other one in Jakarta, they wouldn't even have any interaction. But when they get close, enough, see, when the molecule are far away and they get close, they begin to feel interactive forces between them. And the first forces that they will experience is first attractive force. Now that will be very interesting when we look at how they create, or what is it that caused the attractive force. It has to do with how the electrons are arranging themselves, how to position themselves. So first it's attractive force, attractive, but when it gets close enough, so initially attractive, but when it close enough, when it is too close, suddenly it's changing to become repulsive. Now remember, in physical chemistry, you have the PV equals ZRT, right? Remember that Z? Forget the hat. Z. Z is compressibility factor. For attractive force, do we have Z positive or negative? Remember? Greater than 1, less than 1? Z less than 1, right? For attractive, Z greater than 1 for repulsive. So if it is necessary for you to make a prediction, is it attractive or repulsive within that range? Let's say you have a certain gas, then you calculate the Z and you can determine also, are we in the cooling zone or the heating zone? Because one side will be heating, the other side is cooling. So you have to make sure that you know you operate within the cooling zone. Now we will see that cooling zone is actually happening in here. Okay. Now let's look at this. No, let's look at this slide first. Now let's go back to the molecular level. When we say cooling, what do we measure? The physical properties.
The kinetic energy.
Kinetic, which is linked to temperature, right? Remember, kinetic energy is actually, or rather the opposite. Temperature of the molecule is a measure of kinetic energy of that molecule. So when we talk about temperature, without we realize it, we actually talk about the kinetic energy. The higher the kinetic energy, the higher the temperature. The lower the kinetic energy, the lower the temperature. Now what happened is, in a throttling device, remember, go back to this, enthalpy changes is 0, right? That's why we have the subscript in the partial differential equation. So enthalpy is 0, meaning the total energy of the gas is constant. Okay? So the total energy of the gas is constant, and it comprised of two type of energy, which is the potential energy and exactly what we just discussed. Where am I using? Kinetic energy. So we have potential energy and kinetic energy. So if this is constant, let's say this is 1000 joule. Let's say initially we have 500 and 500, right? Just for ease of discussion, an arbitrary number. So if kinetic energy, if potential energy is decreased, then this must increase, right? So if we have lower potential energy, then we have increased kinetic energy. So meaning if PE increase, then KE must drop, right? Also meaning T must drop. Okay. Same thing the opposite. If PE is dropping the opposite, then kinetic energy must increase and T should also increase. But remember, what we want is this, right? So what we want is kinetic energy drop, meaning this is what we want, right? So we want temperature to drop in an expansion. We want kinetic energy to drop, so temperature drops. Now let's go back to this throttling device. Let's just say if I start at this point here, let's say here, let's say intersection between the circle and the line, right? There. In a throttling device, do we go left or do we go right in this chart? Now, throttling pressure is decreasing. So distance of molecule is increasing. So getting farther, right? So we will move to the left or to the right? To the right. So we move that way, right? So when we do throttling in this graph, we move to the right. So let's go back to this. Let's see which case we have. So in a throttling device, we move to the right side, right? We move to the right. And then we have this, let's say we are in the attractive zone. If we move to the right, what happened to the potential energy? Increase or decrease? Sorry? Are you sure? From left to right? No, it's increased, right? It's increasing, right? So potential is increasing. So exactly we have this case, right? If potential energy is increasing, what happened to kinetic energy? Decrease. Do we have cooling or heating? Cooling. So this, let's say the case PE is becoming 800, right? And this one becoming 200. So that's exactly what's happening. Oops, sorry. I lost my. Okay, so we move from left to right, right? So pressure decreases, potential energy increases in this attractive region. So we have cooling. So that's exactly what we want, right? So cooling indeed is what we get. But let's just say you operate in the wrong pressure zone. You design your equipment in this zone, which is repulsive force zone. What do you think will happen as we go from left to right, right? So the change is massive from left to right. PE is increase or decrease? Decrease, right? So KE will be increase. So if you operate in this region, rather than cooling, you will get heating, right? Heating, you get heating. So clearly, when you design your equipment, you have to know the pressure zone that you have the gas is in the attractive area. So that's why sometimes it is necessary for you to recognize the importance of the value of Z again. Okay, the Z is the measure of also is it attractive force or repulsive, which is dominant. But also the truth is we also have data for each of different kind of freon gases for any gas which you want to use. So in this case, this is a plot of temperature versus pressure. So you will see is it temperature is needed, is it cooling or heating, right? Remember again, for x-axis is pressure, right? So for pressure inside a throttling device, is it from right to left or left to right? Right to left, right? Pressure drop, right? The throttling. So you go that way. So that's why in this case, you when you P decrease from A, let's say, to C, right? From A to C, you have pressure decrease, also T decreases. So you will have cooling. But let's say if you use this gas, and you are still operating in the same pressure zone from here to there. You can see that pressure decrease, but T increase. So you are selecting the wrong pressure zone for your cooling device. The same thing, you are using the same gas, this one, but you select the wrong pressure zone. You operate in here. You expand the gas. In this area, you get heating or cooling, you get heating, right? So it doesn't work. So clearly, when you selected the type of gas which you want a refrigeration system, that is cooling, you have to operate within this region. So that's why it is very important that you have this kind of graph. This one will be more fundamental, so you understand why it is that as the molecules are getting farther away, you have cooling first, but then if you select the wrong region, you will have heating. So you have to operate in this region, and the key is recognizing that, go back to this Joule-Thomson coefficient, dt over delta P, delta T over delta P at constant energy. So that constant energy or constant enthalpy is exactly this constant total energy. Mathematically, we write it that way. And this is, remember, delta is changes, right? In thermodynamics, changes is always final minus initial. So put that in your mind. So you want cooling, that means top must be negative, the bottom is fixed, has to be negative. Why? Because why is it always negative? It is throttling, right? Throttling cannot increase pressure. It will always be decreasing in pressure. So the bottom is always negative, but the top is negative or positive. So you have to just play around which region do you operate, here or there or here or there. So let's say, but I want to have heating. So you select the right region. But okay, you have questions? No? No, I thought you have questions. Okay. So you notice now why the Joule-Thomson coefficient is still the key to designing the refrigeration process. Now we have I think the latest Freon is R32 you recognize in your home. So they must have this kind of graph for R32, which I haven't put right now. And you design the pressure zone as well as the temperature zone so that you are operating exactly in the right area. But one thing which you must understand is how this throttling device can be like a valve or a pros plug uh, result in, where is that equation? This one, right? Delta is 0 because you simplify the equation of mass and energy balance equation, and then you link it up with the fact that mathematically, eventually, this is what we derive. This is something which we took in physical chemistry, actually, if you remember. So that is subscript which symbolize that enthalpy is 0. Okay, now, so that is the principle of Joule-Thomson coefficient and how it is related to a cooling device. You have to select the pressure zone and not the wrong zone for heating or cooling. So I may be asking you, let's say in offset, uh, which area of operation, okay, of course there will be no cooling or heating, right, marking in the graph, but which area will you select for your refrigeration? Here, right? You say here. And then I will ask you again in the oral exam, why? Explain. And then as to why, okay, yeah, this one because this is delta P drop, T drop, right? Why again? Why? The reason why is here. So you have to understand this one. In this area, actually, the molecules are already quite tight, so they want to replicate one another. But this one, the molecule is quite farther away, so they have room to maneuver the electron. So remember, the electron is always moving in harmony, so the result is attractive force rather than repulsive. But if the molecules are too close, there is not much room to maneuver for the electron to place themselves. So they begin to have dislike among each other, and they begin to um, what to repulse. Okay, so you have to tie up this with your physical chemistry class. Okay, so that's the throttling device, Joule-Thomson coefficients, and the refrigeration process, and how it is linked up with the distance between molecule. When we expand, when we compress, temperature drop or temperature increase, and you also go back to the fundamentals, which we discussed very early in the course. Okay, so I think that's that. So remember the term isoenthalpic. That was your question, right? You were asking isoenthalpic. There's isoenthalpic. There's isentropic, isobar, isotherm. So those terms must be put in your mind. So it's sometimes they discuss constant enthalpy, but they say isoenthalpic. What does it mean? Should be. Okay, so thank you. So I think that's that. My review about the Joule. Okay, thank you.